but I remembered luckily. Okay, so it should be recording now. It looks like it. So here we go. I want you to find the antiderivative of ln x, and I think we might have talked about this last week, or maybe it was the beginning of this week. I don't remember, but somebody, and I don't remember who it was. Sana, was it Sana? Like knew what it was because you'd done it in high school, or maybe it was somebody else, and I'm misattributing that. Mika, was it Mika? I don't remember. It was one of you had done it in. Was it you, Mika? Was it you? Wasn't you? Was or was not? Yeah, it was you. Okay, good. See, I remembered, right? I knew. Yeah, I know, Sana. Sorry, it wasn't you. It was Mika. Had like done this in high school or something, and so knows what the answer is. Yeah. Was that last week or was that Monday?
It was
Man,
Monday.
yeah. So clearly the days are just blurring. No, I don't know about if that's throwing under the bus. Just misattribution, right? Okay, and everyone, kind of importantly, if you are trying to do this, I don't mind telling you this now because I don't want you to kind of miss the point of this question, but you don't know how to find an antiderivative of this function. So of the four functions that I've given you, your best bet is to just differentiate them and see which, if any of them, give you ln x, right? If you don't remember our conversation from Monday, that's probably a good way to do it. And then next week, we'll show you how to do it.
Oh, exciting.
Mm-hmm.
So then it's next week U substitution and by parts?
Yeah, FTC, part substitution, that whole thing. Yeah, okay, so sorry, I was definitely wrong though. You know what it was though? It was probably like I knew it was a two-syllable first name that ended with That's I'm sure what was in my brain, and so it was between you and Mika. So that's what it was. I don't think anyone else fits. I guess Sarah would have fit that, right? Two syllables ends with an Oh, and Leah, so it could have been you too. And Kayla. Okay, clearly this was not a good criteria. That was definitely just not.
Maybe it was 4 letters with
Four
two
letters. Maybe it was
vowels.
4 letters. Yeah. Yes.
I mean, there definitely are, I'm assuming with Tyler as well, but students that I remember more just because their name pops up much more often in the chat.
Yeah, just like in real life, if you come to my office hours more, I would know you better, right? And actually, there are students who do come to office hours whose names I recognize, and students who talk more in the chat who I recognize more. That's the way it is, right? Okay, so we're stalling around 56%. I'm going to give you all another 30 seconds or so and get in. Yeah, I mean, squeaky wheel gets the grease and all that.
Can't say I've heard that expression before.
Really?
Nope.
Oh. Yeah, I mean, to some extent, it's the only people who will get what they want are those who ask for it. Or alternatively, you have to complain in order to get what you want, sort of thing, which is not a take on that I like. Right? I'd rather be like,
So that take seems kind of Karen-y.
Yes, yeah, very much so. But again, there's like some underlying truths to that, right? Okay, so we're at 73. That's an okay number. We'll share the results here. So wow, that's a pretty even split, which is a little bit concerning. So this is the sort of thing, remember, you can just differentiate, and whichever of these functions gives you ln x is the right one, and yet we got a pretty even split here. So you made me do this. Just remember, I didn't.
Way to blame shift there,
Oh,
Tyler.
wait, don't go. There are no rooms. I need to recreate the rooms. Recreate. Yeah, you're going to breakout rooms, right? All you had to do is differentiate and see what you got. The law next. That's right. To the gulags with you, Northern Siberia. It's only been 50 people for like 2 weeks of Durban. I have no idea what's going on. Just
Tyler's sending you all to your room.
that's right. It went from like 100 to 50 in a week. That's true. That is true. I don't know what happened. It's okay. It happens. If everyone's learning and doing well, I am not upset, right? Yes, that's true. It was last week's, but I don't know what's going on with this week. Like maybe we just haven't gotten the back, or it's possible that people have realized that they can study and do fine without interacting. And if that's the case, fine. But right. But yeah, I guess this sort of thing that's like, what we want, what we really want, what our goal is that we want students to be able to get it, like try questions with me and Jordan here so we can like answer questions, to do questions with us around so that when you make mistakes, we can help and fix. And if you have any questions, we can answer them. But I think some students just don't want to engage. Right? Because they like won't even try and answer. I know that whenever I open the poll, somebody just guesses it. One or two people just guess at random immediately, right? Because they rarely get the correct answer, and they do within the first couple of seconds. But in that case, like I'm not certain what even is it. You, Sarah? Are you just guessing at random? Because I don't. But why? Why? Like the whole point is that I want you to try, because if you try and you make a mistake and then I help show you why the mistake was there, but then you might as well just watch the video, right? Though I get, sometimes you do ask good questions. And so I'm definitely happy to have you here. But, that's true. It isn't always me. Okay. But yeah, right? The goal is to have you try, make a mistake, or if you get it, great. But if you make a mistake, then when you see the correct way of doing it, that's more valuable than if you just see the correct way of doing it immediately. Do you know what I mean? That's the idea. And we know that that works pretty well. So that's sort of what we're going for. That's true. That's fair. Right. Yeah, that's true. A 1 a.m. for you, it'd be different, right? Because it's only like 5 p.m. for me. So that's fair. We can definitely have a pass for a 1 a.m. lecture. I definitely never had to do it, so I can't even begin to think about what that must look like for you. Yeah, and I don't have good news about next year either, so. Oof, that's rough. Yeah, being exactly 12 hours off is about as bad as it could be, I think. All right, so we're going to start bringing people back. We'll vote on this again. Oof. Oh, wow. Okay, that's good. Lots of good answers coming
in. One of these days we'll get 100% on one.
I don't think so. I think, yeah, it's always the fan. It's stupid. Zoom. I've shown you it, right? Like what it looks like, what Zoom looks like. Hopefully you can still see the question. But look at this. It's all Zoom. Right? Of my top processes, it's all Zoom. Like, what do you do in Zoom?
mean, at least the name is accurate to what it's doing to your fan.
Yeah. It's very, yeah. Oh, we're already at 75%. That's pretty awesome. Okay, so let's do 15, 20 seconds for any last people who want to just come in. Oh, wait. It's just all of a sudden see a terminal on your screen. That's fair. I didn't even think about that. Yeah, I mean, like I just try to use the mouse as little as possible. I don't know about you guys. I hate the mouse. Get to the chopper. All right, take a look at this.
Shortcuts.
Yeah, not even shortcuts. That's just how my thing works. But yeah, I'll show you one day. But okay, so please work, pen. Please work. Thank you. Yeah, and Mohammed, I don't know about you. Like, I'm also running polls and sharing my screen, right? And like running breakout rooms. So doing all that stuff just really kills the computer. Okay. So we're asked to find an antiderivative of ln x. So we want an antiderivative for ln x, right? And remember, that means we want a function which differentiates to ln x. So we've been given the following functions. So, the first option, this was A, was f of x equals 1 over x plus 3, okay? And if this is an antiderivative, that means that if I differentiate it, I'll get out ln x. But that's definitely not going to work, because if I differentiate this, I get negative 1 over x squared, and that's not f of x, right? Okay, so that's not an antiderivative. The second option, 1/2 ln x squared minus 10. Oh, sorry, the squared's on the outside. Okay, so if I differentiate that using the chain rule, I'm going to get ln x divided by x. Okay, that's also not ln x. It's close, right? But it's not quite there. For C, we had f of x is ln. Now the x squared is in the inside, plus 5. And in fact, we can do a little bit of simplification there. We can pull that squared out just to write it as 2 ln x. So now if I differentiate, I just get 2 over x. That's not ln x, right? And even just, by process of elimination, it's got to be the last one. But let's check it just to make sure. So we've got x ln x minus 4. And again, all these constants don't matter, right? Like in the top one, you're not worried about the 3, and the second one, you're not worried about the 10, the 5, the 4. None of these things matter. It's only the only thing that matters is, right, the meat and potatoes of it. And so if we differentiate this one, okay, so we're going to have to use the product rule. So derivative of the first, so let's work on this function. Derivative of x times ln x, that's just ln x. That's a good sign. Plus the derivative of ln x times x. So that's x over x. And then minus the derivative of x, which is 1. And something cool here happens, right? Like we get 1 minus 1 here. So that whole thing is just 0. And that gives us ln x like that. All right, so that one works, right? This is the right answer. That's the one that gives us ln x. That was my check mark. And so that is an antiderivative. So here we just, yes, exactly, Haysom. So you actually might have come in a little bit late maybe, and you might not have heard me say that. So I said for this one, I really do want you to use the multiple choice because I haven't shown you how to find the antiderivative of this one yet. And so you had to use the multiple choices and just differentiate them and see which one you gave me, gives you ln x. Can we talk about B again? Sure. So B, right, was 1/2 ln x squared. Let's not worry about the 10. Okay, let me just kind of skip the 10. So if we differentiate, so I will get, so d dx 1/2 ln x squared. So that's going to be 1/2, right? Let's just factor the half out. Let's not worry about it. Now I've got ln x squared, right? This is a composition of 2 functions. And let me know if this is bugging you. I can go into it in more detail. but it's going to be 2 ln x times the derivative of ln x. Right? That's going to be the chain rule. Because here I've got the functions, right? One function is x squared. The other function is ln x, right? And so f of g of x is ln x all squared. Oops, sorry, let me get rid of that. And so when I differentiate, I'm going to get the derivative of x squared, which is 2x, but evaluated at ln x. And then I'm going to multiply by the derivative of the inside, which in this case was ln x. So the 1/2 and the 2 will cancel out. The derivative of ln x is 1 over x. And when I did it, right, I just combined those immediately and wrote it as ln x over x. But the 2 is outside. Oh, but it is x squared, right? So let's look at, so remember, f of x is x squared, g of x is ln x. So f of g of x is f of ln x, or maybe I should put it's g of x squared, right? Because f of x is x squared. And then if I plug in g of x, I get that, right? So that the difference between b and c, say, right, with c, the x squared was on the inside. So that would have been actually the opposite composition. So instead of f compose g is b and c is g compose f, right? So g of f of x would have been ln of x squared. Does that make sense? Or do I need to go through it a little bit more, or are you okay with that? Okay. All right, let me think then. What can we do? So let's just kind of do it in general then. Okay, so once again, we've got f of x is x squared, right? And let's not even let g of x, might be helpful to put the ln x in square brackets. Yeah, sure. Okay, yeah, let's do that. So that's a good idea, Jordan. Right, that's the function that we're working with, right? It's ln x in brackets, and then we're going to square the whole function. So I've got f of x is equal to x squared, and let's let g of x just be g of x. Let's not let it be ln x or anything. Let's just let it be some sort of function. Okay, so what that means is that f of g of x is equal to g of x squared. And then if I differentiate, I'm going to get f prime g of x, g prime of x, which is going to be 2 g of x, g prime of x. Right? Does that make sense? Right? And there's no lns or anything here, right? We're not using any logarithms. This is going to be true for any function g of x that we want to use. So is that okay? Does that make sense? Okay, cool. So now let's let g be ln x, right? And all I'm going to do is everywhere I see g and g prime, I'm going to plug that into here. So I'm going to get 2 ln x times the derivative of ln x, right, which is 1 over x. Right, and that's exactly what's in the square brackets up here. I'll try and make it clear what I'm pointing to. Right, that's 2 ln x, 1 over x. So hopefully that makes sense and everything's good. Okay, are there any other questions? Is everyone okay? All righty, I'm going to assume yes. And let's do another question then. So here's one. Now I want to say for this one, be a little bit careful, okay? Lots of students, the first time they do this question will make a silly mistake. So just, think it carefully, think about what it is that you're doing. And I think I did do an example like this in the video as well. Yeah, it's not I don't think it's a trap. It's just I know that there's a common mistake that students will make here, and it's good to catch it early. Prof, don't we multiply 1 over x by a half? I mean, in the original function, there was a global factor of a half in front. That's true. But if you're just differentiating ln x all squared, there's no extra half. So I'm not, did you mean in the original function? Because the original function did have a half in it. All right, I will assume that a fairly lengthy response is forthcoming because it was 1/2 2 ln x. Okay, so times, it's 1/2 2 ln x times the derivative of ln x, right? Not plus. But yes, that half does go into it. But let me see. Right, when I was doing it, I was just differentiating ln x squared. I wasn't worrying about the half. Right, so that second part was me just doing ln x squared, not the 1/2 ln x squared. Yes. Yes, after differentiating, I would multiply it in if I was doing 1/2 ln x squared. I would multiply the half in, which if you check, I did do originally when we first did the question. So you didn't multiply 1/2 to the derivative of ln x. But remember, it's multiplication, right? So you originally, in 2 lines above in the direct message you sent me, you wrote 2 ln x plus the derivative of ln x. It's not plus, it's multiplication. So when you multiply 1/2 times AB, that 1/2 can go in front of either of those terms. But if you did 1/2 times A plus B, you need 1/2 A plus 1/2 B, right? So it's not addition, it's multiplication. Right here, maybe let me type it in so that. Oh, that's weird. Stupid Zoom not letting me copy and paste. And don't forget, if you guys want to use a calculator to help you do this one, you absolutely can and should. In particular, for those of you who maybe have or have not gotten there yet, you are, of course, free to use Octave if you want to. Yes. Yes, Hazel. That is exactly what we're asking for. But you kind of need to know like C to know the answer, right? You can't just get D. No, there is not. Usually people think there's actually too much information in the question. Can you speak about what you think might be missing? Well, if you got something and it's one of those numbers, that's a good sign. F prime of 4 or F prime of 1. So those are options. It is possible. So basically, you need to be given two pieces of information, right? And I could give, and one of those pieces of information has to be about F. So I can't give you two pieces of information about F prime, but I could give you two pieces of information about F, or one piece of information about F and one piece of information about F prime. So the fact that I've given you two pieces of information about F makes it possible, but does make it a little bit harder. It might, I don't remember what I did in the video, whether I did two conditions on F or one on F and one on F prime. I feel like in the video I might have done F and F prime, but I could be misremembering it. Okay, two on F, okay. But I might have made it one of them like a condition at 0. Yeah, exactly. Yeah. So if one of the x's is 0, it makes it much quicker because you can figure out one of the constants very, very quickly, right? But in this case, because neither of them is 0, it makes it a little bit harder. Okay, so we've been going for a while on this one. We're almost at the 9-minute mark, actually, but only 33% votes. So I'm going to say, let's do one more minute, see if you can wrap it up in that time. And we'll stop at the 10-minute. We won't do breakout rooms because we've already spent a long time, but this one is a bit computationally longer. So I'm fine giving you that time. Okay, 30 seconds. It's all right. It's okay. Okay. And 3, 2, 1, 0. At least we got over 50%. I'm pretty happy about that. And we're leaning a little bit in the B direction. B is the correct answer. So B is what we want here. So the answer is 1. At least last time I worked it out, it was 1. But we'll go through it. You guys we'll see if I made a mistake. Oh, well, I'm doing as long as you know you got 1, that's fine, right? Like it doesn't matter. Even if you just missed the pool by like 10 seconds or something, it's not a big deal. Okay, so we are told, so we know that f double prime of x is 15. I wrote it as square root x. So let me write it as x to the half, just because that's going to be a little bit easier for us when we actually choose to take the antiderivative, right? So I'm just going to leave it as x to the 1/2 there. And then we're told that f of 1 is 0 and f of 4 is 109. And you know what? Usually it's a big clue. When you see ugly numbers like 109, probably we chose that to make the numbers work out, right? So the first thing we're going to do, let's find an antiderivative of f double prime, which will give us f prime, right? So we're going to anti-differentiate. And when we do that, we're going to get f prime. I'm not going to worry about the 15. Somebody tell me, what is an antiderivative for x to the 1/2? Very close and young. You want, so you got the x to the 3/2 in there. And yeah, exactly. There you go. 2/3, right? Don't forget that constant in there. Perfect. Exactly. Because you need, right, whatever the fraction is, you need the reciprocal of it so that it cancels when you take the power rule, right? And you can see the math is going to work out very, very nicely. 2/3 of 15 is 10, right? So we're going to get 10x. Oh, sorry. Forgot the thing that I needed. And then we're going to put in a plus c, right? 10x to the 3/2 plus c. Yeah, don't forget the c here, right? And so this is the common mistake that lots of students will do, is they're so used to kind of, and we saw this, all the time, is, well, actually here, let me do the next step and then I'll kind of say this. So we're going to anti-differentiate one more time to get f of x. Okay, so I'm just going to factor out the 10. So now what is an antiderivative for the x to the 3/2, right? This is an antiderivative for the x to the 3/2 here. So what do I want to put? 2/5 x to the 5/2, great. 2/5 x to the 5/2, right? Plus, now an antiderivative for c is cx, right? Oh yeah, perfect. Shifeng kind of ahead of me there. And then we put in another constant d, or you can call them c1 and c2 or a and b, whatever you want, right? It's just that we know that they're constants. And 2/5 of 10 works out nicely to be 4. Now, something that I know that a lot of students do, which does sometimes screw some people up, and yeah, don't use the same thing for both constants, Jordan, good point, because that is a common mistake that students will do. They'll call them both c, and then when you try and solve for them, you're somehow forcing them to be the same thing, but of course they could be different constants, right? So great point, Jordan. And what some other people do as well is they'll try to get all the way back to f and then just tag on a plus c at the very end, right? Because that's the way that they're used to thinking. Let's just anti-differentiate. I'm not worried about the plus c, and we'll just throw the plus c in at the very end. But notice that if you only put it in at the very end, you're going to lose this linear term, right? This term that has the x in front of it. And if you omit that term, the problem, it becomes completely impossible to do, because there's no one value of d such that f of 1 is 0 and f of 4 is 109, right? So you have to be careful about that. Now we've got our two pieces of information, right? So you remember what I was saying when I was talking earlier. I said you had to have two pieces of information, potentially 2 on f or 1 on f and f prime. And the reason for that is you have two constants, so you need the same number of pieces of information. Okay, and if the question had told you something about f triple prime, you would have needed 3 constants, and so 3 pieces of information. Or f quadruple prime, you'd have had 4 constants, and so would have needed 4 pieces of information, et cetera, et cetera. All right, so let's plug this information in then. So we know that 0 has to be equal to f of 1. So let's evaluate this at 1. So I get 4 plus c plus d. And then I also know that 109 has to be f of 4. And so that's going to be 4 times 2 to the 5. So that's 32 plus 4c plus 4d. So that's 128 plus 4c plus d. So now I have 2 equations. So now I have two equations and two unknowns. And let me kind of write these more suggestively as, C plus D equals -4 and 4C plus D. So if we subtract 128 from the other side, we get -19. You can solve this however you want, but I think you will get C is equal to -5 and D is equal to 1. How did I get 4C? Oh yeah, sorry, not 4D. You're right, absolutely. I just got caught up there. It's just D. Thank you, Selena. Just D. So when you go through and you solve this system, then you get C is equal to -5, D is equal to 1. And so F of X is 4x to the 5 halves minus 5x plus 1. And so F of 0 is, well, everything with an X in it just dies. And so you get 1. Right? And that was B. Okay, so that's how you do it. Now you could see, right? I kind of skipped the portion where we solved this linear system here, but and it's two equations. It's two equations and two unknowns. You imagine you all could have done that even before we learned linear algebra. On the other hand, if you're thinking forward to something like a final exam potentially, I probably wouldn't do too much of this, but you could imagine that we can make a question where maybe we give you a third derivative and ask you to find the coefficients. And in order to solve it, you would have three equations and three unknowns. And the best way to do that might be to apply a little bit of linear algebra, right? Set up a matrix system. And then, and again, don't solve it by hand. You can plug it in octave. That's totally okay. Sure. And but like, that's totally reasonable. And there's lots of times in real life where third derivatives do actually show up, right? And they'll show up in like things like differential equations, but they do, believe it or not, actually show up. And if I give you four, what if I give you the fourth derivative of a function, right? So now you've got four equations, four unknowns, and you probably really want to use a matrix to solve that linear system, right? So now suddenly we can tie back into some of the stuff that we learned back in the first term with linear algebra and everything in order to help us, solve some of these linear systems. Oh, yeah, that's probably true. How did I get, okay, so I got a direct message saying, how did I get -5 and 1? So, I mean, you can check, right? Obviously, if you plug those numbers in, it does work. The way I did it is I legitimately, you can go through your normal thing of solving that linear system. I plugged it into Octave and asked it to, compute RREF for me, back in the same thing that we did in whatever that was, October, November, when we were learning about linear algebra. I just opened up Octave, threw it into a matrix, and asked it to row reduce, right? So that's how I did it. Where would this be applicable in real life? So yes, jerk. Yeah, jerk is the third derivative. That's absolutely true. So Christine, what happens is in real life, you get these differential equations, right? And that's the real reason why you study calculus, because differential equations, you take the rules of life, whether they be economic rules or meteorological rules or physical rules or whatever the case may be, and you apply calculus them to create these differential equations. And differential equations might look something like this, right? They sometimes look like something like that. And you've got to figure out what dy dx is, right? Like what function y as a function of x satisfies this equation. Well, it turns out when you do this, you'll be able to get it, but there will be two constants that could show up. And those constants appear in the same way that we're doing antiderivatives here, and that you actually have to like plug in and solve for what those constants could be. Right? So for example, a classic differential equation is this, right? And can anyone tell me what is the solution to dy dx equals y? Like just if you had to guess, right? Like not knowing anything about how to solve differential equations, can anyone think of a function such that when you differentiate it, you get itself, right? Dy dx is equal to itself. It's not a trick question. E to the x, perfect. But it turns out more than that. It turns out, actually here, let me use c instead, because that's what we've been using for constants. It turns out c e to the x will work for any constant c, right? Because if you differentiate this, you would also get c e to the x. And that c actually, even though here it's not plus c, that c does show up as a plus c. If you go through and were to actually solve this, you would see why it showed up as a plus c, but then turned into a times c. It's complicated. But you can see here that there are constants which show up. And then if there's a d squared dy, dx squared term, there will be 2 constants. And if there's a 3 derivatives, there will be 3 constants. So this, Christine, is where these things show up, if that sort of helps. So this stuff definitely happens for real. Yeah. All right. And like I said, you can dedicate entire classes to learning about differential equations. They're interesting. They're fun. They're kind of dumb. They're interesting, fun, and kind of dumb. And I say that with the most affection possible. Actually, if we only have time for one more, maybe okay, yeah, maybe let's do something similar. I cheat a little bit here and see. Some of you might just know the answer without even needing to do the math.
You just incorporate physics?
What?
Did you just incorporate physics? This looks like a physics equation.
I mean, it absolutely is, but I didn't state it as a physics question.
Fair.
Okay, but here's the thing. Like, this is what I said. This isn't a class in physics, so I don't want you to worry about it. If you don't know how to do the physics of this, then don't worry about it. You don't need any of the physics in order to be able to do the question as I've set it up, right? But if you do know the physics, you can now see where this equation comes from. You know, Sarah, so the interesting thing is I hated physics as well, and both in high school and in my first year of university, right? And you know why? It's because the physics they make you do is stupid, right? It's a lot of like, oh, you've got a block sitting on a ramp, and you know, if it slides down and the coefficient of kinetic friction is blah, what is, right? Like, and you're like, who cares? And so, but for me at least, when we got into higher level physics, it was much more interesting. So I really enjoyed physics as it got more advanced. But in that case, from my perspective, very much so, that was because it became more mathematical, right? Where do we use calc in commerce? I think Jordan's going to have to answer that more than me. I mean, obviously calc shows up a lot in econ, right? Like,
yeah, it shows up a ton in economics,
right? Marginal blah means take a derivative.
Do I have my equation sheet here? So you'll do some stuff with it a bit in investments and finance too. I think you kind of use it more in 4th year finance courses though. Accounting doesn't really care about it, neither does marketing though. It's more for finance.
That probably sounds right too, even having just talked to some of the accounting and marketing guys. But again, like, yeah, especially in the finance, again, and I think I've said it, right? Like, I was going through Hall's book on derivatives and options pricing. And when you're trying to like compute an optimal hedge ratio, you compute the optimal hedge ratio by like taking a derivative of the standard deviation, right? And so I can speak as somebody who has kind of gone through some of that material that for sure it showed up.
Well, right? Unfortunately, we don't have a class on stonks. That's just memeing.
And I didn't get a chance to do it, but if any of you want to, you can go back in the book and look at the end of the linear algebra section. I do a little bit on options pricing. And then I think at the end of the probability section as well, I do some on like binomial modeling and obviously Markov chains and stuff like that. And then Markov chains does have some calc in it as well. So you might want to check that out.
Yeah, I think your finance application questions at the end of those units were actually from the assignments in my year.
Yes, they were. So yeah, if you guys want to see that, go and check those out. You know, I'm always looking for more examples as well. So as you guys get into higher years and you see some of these things, you know, you should email them to me and be like, hey, listen, you know, you said you wanted to see some of these things, send them to me. The problem, of course, is that most of the examples I find are just like so ugly and disgusting that I'm just like, this isn't, you know, I'd spend like half an hour just explaining what some of this notation means. It's not a nice example. So our focus here is more of, you know, get you comfortable with the tools and the intuition and understanding what a derivative is and how it's useful, with the goal of that when or if you eventually do see it, you'll just know what it is that it means, right? And so you can kind of jump straight into, you know, doing stuff kind of correctly. So that's the idea there. Because same sort of thing, actually, we're going to do a lot of integration, right? And we're going to do 3 weeks of integration, but I'm not going to give you any applications of it other than kind of, you know, stupid area questions. But the thing is, it does show up, and it shows up a ton in applications. It's just that most of the applications I could give you are either A, not interesting, or B, too complex, or C, are the sort of thing that they are going to worry about in a future class. And so I don't want to waste a bunch of time worrying about it here. So you guys might look at it and be like, well, why is he teaching us this? And it's so that when you see it in a future class, it makes sense, right? Yeah, exactly, right? Like, right? Because yeah, what is it? You can like draw the supply curve, you draw the demand curve, and you're trying to like compute the areas between these two curves. It's in the notes, right? You guys, you can see it in the notes. Or it says there's an explicit thing that says applications to like finance and economics or something, and you can look. Oh, you could do like continuous investment. So if you guys want to go back into financial math, we can use integration as we're about to do over the next 2 weeks to do what happens if you're investing continuously now. So not just compounding continuously, but investing continuously as well, whatever that means. Right?
Supply and demand curves still bother me.
Yeah, you know, I'm just very thankful that I don't need to worry about that stuff. I'm not gonna lie, I've never been
Like how ass backwards is it that the independent and dependent variables, for whatever reason, just for that graph, are switched?
I don't know what to tell you, man. I don't know what to tell you. Just like,
Because then even other types of economic graphs have the independent on the horizontal axis and the dependent on the vertical, but for some reason, supply and demand graphs, we just got to switch it up.
maybe there's a reason, but I couldn't tell you. All right, I have no idea. You know, there is I can tell you something that I've heard from friends. So I had a couple of friends. By the way, we're at 65%. So let's do another 30 seconds or so, and then I'll take this up. Looks like we kind of overwhelmingly have the right answer, which is great. But, you know, I had not a lot, I'd say like 4 or 5 friends, though, who were doing grad school in economics. And they told me this very interesting story, which was basically that, you know, there's been this trend in economics that, you know, they should do more math. And, you know, the more rigorous mathematics that's involved, the you know, the fancier the paper is, the more likely it is to get published, and yada yada yada. But it comes at a cost, namely that, you know, they were talking about the mathematics that these people are using to model these economic situations don't predict reality, right? So they construct all these wonderful mathematical models, but reality doesn't resemble these mathematical models. But nonetheless, people are kind of building things off of this. And in some cases, I guess policy decisions are being made off of this. Well, it's not to say that math is bad, but that like it sounds like the economic community is heading towards trying to use as much math as they can. And that's great. But I mean, you should reject models that don't model reality. Do you know what I mean? Like, the entire point of economics, I think, is that it should model reality. And so if it doesn't, that is true, that's fair. But like, if it shows that your math doesn't work at all, then you should throw it out, right? Don't like build on that theory. Now, I don't know much about this. This is just, I've seen some of my, you know, economics friends in grad school who kind of rant about this. But that is just kind of a thing to keep in mind. So, you know, just be aware of that. But that being said, I've met also a fair number of economists who are really bad at math, who want to use fancy math, but are not good enough at math to do it. And so there ends up being a little bit of some scary stuff happening there. Okay, so overwhelmingly, our answer is B, and we got a nice 76% number, which is consensus, and B is absolutely correct. Now, again, you don't need to know the physics of it, but hopefully you guys have seen this. This is kind of like that classic thing. If you take a ball and you hold it a height y naught above the ground, throw it up with an initial velocity v naught, then this function f of t describes its height as a function of time. And if you were to graph this, you get this kind of classic parabola, right? But you don't need to know any of that in order to actually be able to do this question. It's kind of like what I just want this to do is to be a nice example of, maybe some of you saw this in high school and maybe you didn't know where this equation came from. And now, oh, it's just simple application of anti-differentiation, right? So again, we know that f double prime of t is equal to negative g. And there's a physical rule for that reason, right? F prime of 0 is v naught, and f of 0 is y naught, right? Okay, so we're going to start taking antiderivatives. And again, remembering each time we take an antiderivative, we need to include a constant. So negative gt plus a constant, right? Because g is a constant, right? It's not like some fancy number, it's just a constant. And then if I take another antiderivative, I'm going to get negative 1/2 gt squared plus ct plus d like that. Okay, so now I have my two pieces of information here. And I'm going to plug those in to figure out what c and d are. And the great thing here is if you are given information about f prime, that's great because f prime, in our case, only has c in it, right? There's no d. And so what that's going to tell me is that I'm not going to get a system of equations, right? I'm just going to be able to solve for c on its own. And then once I have c, I'll be able to solve for d on its own. How do we know what f of t is, like in this case? So I anti-differentiated f prime, right? So maybe let me do that again. So I'm going to get negative g, and then I'm going to find an antiderivative of t, right? And by our table of antiderivatives, an antiderivative for t is t squared divided by 2, right? And then I'm going to take an antiderivative of c. C is just a constant. So an antiderivative for it is just c times t. And then now that I'm done, I have to throw in one more constant. Does that make sense? All right, and that's the same thing as, okay, great. All right, so now let me use this condition here. So this tells me that v naught is f of 0. So I'm going to plug t equals 0 in, and that's pretty nice. That works out perfectly. I don't have to solve any equations. I plug in 0 into f prime, and it just gives me what the initial, it tells me what c is. And then I'm going to plug that into here. So y naught is f of 0. Well, everything dies except for d. And so that's pretty nice. So thus f of t is negative gt squared over 2 plus v naught t plus y naught, right? And you're done. So that's all there is to it. And again, for those of you who have seen this formula before and were wondering where it came from, that's it. That's all there is to it, right? It's just an initial value problem. Though you might have to wonder like, oh, why is this true? Why is f double prime equal to negative g? There's physical reasons for that, but that's the idea there. Okay. If everyone's okay, I do kind of just want to do one more. Of course, if you want to, you can leave. That's not a big deal. This is technically the end of lecture. But yeah, I want to do at least one more. Let's take a look at this. And I'm going to give you a minute or so to think about it on your own. Yeah, for sure, which is awesome. I'm going to give you a minute or so to think about it on your own, and then I'm going to give you a hint. So if you, after a minute or two, you don't know how to do it, I'll give you the hint, and maybe that will help. Well, Sarah, you absolutely can go to bed knowing that this will be recorded and that you can watch the recording, and I'll probably post it tonight. So you go to bed, wake up tomorrow morning, and you can watch this. Or not tomorrow morning, I guess this morning for you. Just later in the morning. Yeah, I mean, like, I don't have great news. You know, from internal sources, the admin is saying that we're going to try and return to in-person in fall 2021. But the mathematics don't seem to make sense. And so I think that we will almost entirely be remote in fall 2021. And some departments will be entirely remote all of next year as well. So for those of you for whom time zones are not a great deal, it doesn't necessarily look promising next year. Yeah, I mean, and some people will be fine with that, but for some people, you know, it's not going to be okay, right? Like, yeah, and absolutely. I mean, lots of people are talking about taking a gap year, right? But yeah, I mean, poor Sarah, it's like 1 a.m. there, right? Like, what do you do? And some of you, I think, are just as bad. In some cases, right? Like, oh man, who else is in a really bad place right now, right? So Mika, at 6 a.m., which isn't impossible, but it's not terrible.
I think mainland China is exactly 12 hours ahead.
Right, which is pretty bad. But actually, you know, like, okay, so yeah, Jude, 1 a.m., yeah, midnight. Oh, so Hazen, that one's nasty. 3 a.m. Yeah, I think that's got to be the worst. Like 6 a.m. I think is not bad because we're a later class, but that's got to be terrible if you have a class at like 2 or 3 a.m. Right, which could definitely happen. Yeah. Yeah, that's nasty. I guess you just kind of have to put yourself on like our time zone, right, and just shift your entire life to that. Ugh. Yeah, that's gross. Yeah. Yeah, that's really too bad. And like I said, you know, I hope we go back to in person. You guys get a chance to, you know, come and enjoy
Tyler's lectures.
Yeah, but I'm not certain it's going to happen. The admin thing seems to think that it's going to happen. I really don't think it's going to happen. Yeah. Oh yeah, by the way, the hint for this. So if you look at this thing, it looks kind of like a product rule, like the result of a product rule. So what I want you to do is, if you're still kind of struggling with the answer, think of it like if the thing on the right were the derivative of a product, right? So it's the derivative of the first times the second minus derivative of the second times the first. What would that product be? Like, what are the two functions there? And maybe that'll help you. Oh yeah, that's true. The term tests start at 3. Yeah, I don't know what to say, everyone. It's just it's not a great situation. And even to think about the fact that some of you will be potentially third year the first time you step foot on campus is kind of crazy.
3 years of students trying to figure out where the hell their classes are.
Yeah. Yeah, what a mess. I mean, I can make it worth attendance, but I don't like it when teachers do that. I am very much of the belief that, you know, if you think that you can succeed without coming, and we record the lectures and all that, I think it's perfectly possible and reasonable, that I shouldn't force you to be here, right? That you should be allowed to, and especially if you potentially have this class at 3 a.m., I don't want to force you to be here, right? That doesn't seem fair. And so, you know, I don't like that policy of giving like attendance marks. And like I said, I don't like it when it's fair game to assume that students would show up. And I like it even less when this class is potentially at 3 a.m. for some people, right? Mm-hmm. Yeah, so I guess, Daniel, you're kind of seeing that firsthand. And then what's the point of that, right? Like, all you did was disturb the student's sleep because they had to get up and log in and then check out, right? Like, so what was the net benefit of that policy? Is that you made your students wake up and disturb their sleep. So that's a bad policy, right? That's what I think, at least. Okay, so we're at about 6.5 minutes, but we only have a quarter of the votes. So I'm going to give us about another minute and a half, let's say. Minute and a half. Let's see if you can finish this. Okay, it's 10 seconds. All right, so we've only got about 50% of the votes. That's okay, though. And they said the answer was A. I honestly don't remember if that's the right answer. I think it is. We'll say by democracy it's the right answer, right? But we'll work it out, and then we'll figure out whether it's the right answer. I hope it is. Well, we'll find out. Okay, so let's do this. So like I said, kind of the trick here is to recognize whatever this is. Okay, so what's the question? G of x, G prime of x is 1 over x f prime of x minus 1 over x squared f double prime of x. And, oh, sorry, just f of x, not f double prime. And you're told f of 1 equals 1 and g of 1 is equal to 0. So the trick is f prime of x is equal to 1. I'm not certain what you're saying, Jifeng. Yeah, I'm not 100% certain. But anyway, so what I want to do is I want to recognize this as the derivative of a product, right? So to me, I see this and I'm like, oh yeah, it looks like a product rule. And I can just kind of see, right? It requires a little bit of cleverness, but I can see that this is the derivative of 1 over x f of x. Oops. Do you agree? Do you all see it? Right? Because if I differentiate, or maybe let me write them in the if you want, you could write them in the opposite order, which is maybe a little bit more conventional for how we do it, right? Because that would be the derivative of the first times the second plus the derivative of the second times the first, right? And that gives you the same answer. Okay, so what that tells me is that g of x is f of x divided by x, and then we can't forget that constant plus c there, right? Now, in order to figure out the constant plus c, well, again, I'm going to use the piece of information that I've been given, which is g of 1 is equal to 0. So I'm going to plug that in. So 0 equals g of 1. So that's going to be f of 1 divided by 1 plus c. And if I solve that, I get that c is equal to negative f of 1, and f of 1 is equal to 1. So c is equal to negative 1, right? So thus, g of x is f of x divided by x minus 1. And what do we ask for g of 2? So g of 2 is f of 2 divided by 2 minus 1. And was that A? Yes, that was A. So if you said A, then you got the right answer. Okay, so it's a matter of, again, kind of doing this thing where we recognize that this is, you don't understand how I got the, like this, let me, this part right here. Right, a certain amount of that is just cleverness in this case. Yeah, it's basically reverse product rule. Is that I looked at the line above and said, look, I'm seeing f prime of x and f of x. So one term has f prime, the other term has f. And then one term has 1 over x, and the other term has negative 1 over x squared. So it looks as though, right, that I have the derivative of f here, and I have the derivative of 1 over x in the next term. So that said to me that this was a product rule. And just by thinking about it for a little bit, I was able to see what it was a product of. And unfortunately, that's kind of what you have to do with derivatives, because it, you know, there isn't that nice formula. You sometimes have to be a little bit clever, right? So that was the yellow part. Well, so there's lots of yellow parts. So this yellow part, the yellow cloud, or the 0 equals g of 1 equals f of 1. Okay, sure. So, okay, so at this point, what have we done? So at this point, let me even just kind of like maybe get rid of this part so we can't see it. So at this point, we figured out g of x is f of x divided by x plus c, right? I said, look, if I differentiate f of x over x, I get the correct formula for g prime of x. And we know that antiderivatives, we've got to put this plus c in here. Now I want to figure out what the constant is, right? I want to figure out what c is. So what I'm going to do, just like with the previous two questions, I'm going to use this fact right here, right? The g of 1 is equal to 0. Right? So I haven't done anything there. I've literally just copied down the information in the yellow circle at the top of the screen, and I've just rewritten it there. But now I'm going to actually plug 1 into g of x, right? I'm going to plug 1 in, and that's going to give me f of 1 divided by 1 plus c. But I know what f of 1 is, right? So that gives me 1 plus c. And now I can solve for 0. I have 0 is equal to 1 plus c, so that tells me that c is equal to negative 1. Does that make sense? Hole 13. 5. Is that an okay, though, that like it makes sense? Because sometimes people say okay, but still have questions. Okay, great. Okay, any other questions about this? Zoom out? Sure. Here, let me move this bottom portion back up. And I mean, that's the whole question right there, right? Where that horizontal line is there, Kevin. That's where that question starts. I mean, I can do another one if you guys want. I do have one more. But otherwise, that was the last question. We can kind of go into office hours. I mean, cleverness, like anything, is a skill that comes with time. And you can be clever in one field and not clever in another. And it takes time to develop mathematical cleverness. Like, that's not an obvious or easy thing. But it's the sort of thing that, like, as you see other people's tricks, you know, you begin to gather those tricks yourself. Now, I would say that in this case, this is not the sort of question I would ask you on a test, right? Because I think you all know I'm not interested in testing cleverness. Cleverness is not one of my objectives for you. I'm not interested in seeing whether you know, how clever you can be, because cleverness is stupid, right? A student can have 100% understanding of the class and just not see the clever trick that they need to do, and so not get the right answer. And that's dumb, right? That's not what I want to do. Right. So that's not my objective. That's not what I want you guys to do. So, you know, I'm not going to ask you a question like this, but I do think that this can be valuable nonetheless as a poll question, because it gets you thinking about, oh, as we start to take antiderivatives, we might need to expand our repertoire and see if we can, you know, build in the reverse product rule or the reverse chain rule and things like that as well. And this is going to, you know, we're going to use this as a jumping off point to segue into integration by parts and integration by substitution, which are the things that we're going to do next week. Okay, so that's the sort of things that we can do. Yes, absolutely, a final exam question. I mean, trust me, there's no upper bound to how hard I could make this course. But again, this is just not a thing of interest for me, right? Like cleverness especially is not, I know what it was like to write clever tests, okay? Because you know who the worst people are for asking you to write clever tests? Math profs. Math profs are the worst. Why? Because we're all clever. We've all learned a ton of clever tricks. And a lot of us like to torture our students. And so I know I've been someone who's walked into a test, was confident I knew everything very, very well. And then there were 6 questions that required cleverness in front of me. And that was 100% of my final exam. And that's a BS final exam, right? That's nonsense. That's stupid. And so like, I'm not going to reciprocate. I'm not going to do that to my students. There are classes where cleverness is an objective, and that's fine. This is not one of them. Right, and that's how that is. Yeah, and there are still some tricks you have to know. Okay, so let me do then. So I got a request week 5 poll 13. So let me just pull that up. Give me a second here, because I obviously don't have it memorized. Week 5 13. Find the derivative. Okay, so this is week 5. 5 polls, question 13. Week 5, poll 711. Okay. All right, so this question says find the derivative of x to the x plus x squared. Okay, so this is what we want to do. Now, x squared, we know how to differentiate, right? The derivative of x squared is 2x. So let's just focus on the derivative of x to the x. So we know that the derivative of x squared is 2x. So let's find the derivative of x to the x. Okay, so to differentiate, what I'm going to do is let's set, you can call it f of x if you want. I'm going to just call it y. Set y to be x to the power of x. And let's take a logarithm of both sides. So ln y is ln x to the x, which is x ln x, right? I'm going to take that x in the exponent, and I'm going to pull it down in front of the ln x. And now I'm going to differentiate both sides. So differentiate. So now don't forget, when I differentiate this side, right, I'm going to get 1 over y times y prime. And then when I differentiate this side, I have to use the product rule. So I'm going to get ln x plus the derivative of the first times the second plus derivative of the second times the first, ln x plus 1. Okay, and now I'm after y prime. That's what I want. So I'm going to multiply both sides by y. And that's x to the x ln x plus 1. Okay, see Asana? Okay, so now I have the derivative of x to the x, right? So the derivative of x to the x plus x squared is, well, it's the derivative of x to the x plus the derivative of x squared. All right. And then that's x to the x ln x plus 1 plus 2x, like that. And that is one of the options in the polls, right? That's option A. Now, the entire point of this question is to try and get you to fall into this trap, because a lot of students will do this, okay? So a lot of students, okay, don't do this. So a lot of students will try and set y to be x to the x plus x squared, and then they'll take ln of both sides here. Okay. And the thing is, right, exactly. Yeah, exactly, right? You tried to take ln of everything. So this was exactly the trick that we were trying to get you to fall into, because, and again, the hope is to get you to make this mistake now where it doesn't count for anything instead of later, right? Because the thing is, at here, you can't do anything, right? Some students will write down this. This happens a lot, but this is wrong. Right? That is wrong. Don't write that down. Ln does not work like that. You don't have an identity which tells you can do that. So you get to this point, ln x to the x plus x squared, and you can't do anything, right? And this is a common sort of pitfall that a lot of students fall into. But again, the idea here is that you don't need to differentiate the whole thing, because you know how to differentiate x squared. So just remember, oh, if I differentiate each of them separately, that's the same thing as differentiating them together, right? So hopefully, right, exactly. Yeah, so that's not true. So this is exactly the sort of trap that we wanted you to fall into here so that it doesn't happen later, right? Okay, so one time I was doing MAT133. I was teaching it downtown, and that class at the time had 1,800 students. And I was the instructor who was marking the exam question that was basically this. And the number of times that I saw a student do this, I think about 90% of the students wrote this down. Okay, in 1,800 students, right? And I want you to think about what an absurd number that is, right? What does that end up being? Like 1,620 students. So I saw this 1,600 times. And let me tell you, over the like 16 hours that I was marking, because I saw that it really goes to show you about brainwashing. I saw this so many times, I began to question whether it was actually true or not, right? Like maybe it's true, because if you see this 1,600 times, you're like, well, maybe I'm the one who's wrong, right? And so it eventually actually started to get to my brain, and I had to keep looking it up to make sure that I wasn't crazy. So let me tell you, right? A lot of students make this mistake, but let's get it out of the way now before we get burned on it later. What if it was x to the x plus m to the x? Do you solve each? Yeah, you still do it each one separately, because it's not gonna. Well, is there anything we can do there? Let's try. So that's an interesting question. So what if it's x to the x plus m to the x, right? Well, there's nothing we can do. We can't smush those together just because their exponents are the same. We can't do anything, right? So in this case, we'd still have to do each of them separately. The only time you're going to kind of be okay is if you had, like x to the x plus like x to the, it basically has to be, x to the x or something like that, right? And then you would write this as, oh, well, that's just 2x to the x, right? Then it would be okay. Then you could smush them together. But as a general rule, there's a very few situations in which you'll be able to handle that with a single logarithm, right? Prof, is it true that we can only use ln to bring down the 2x from x to the x when we use the power? Yes. Yes. So my question, no problem, everyone. So the question I have is, we have x to the 2x, and that would be 2x ln x, and then we use the power rule. Yes. Yeah, and that's true. And so if you wanted to differentiate x to the 2x, this is how you'd have to do it. But if you had x to the 7 or something, right, you can just use your normal power rule to do it. So the important thing, you have to use this log trick if there's an x both in the base and in the exponent. Okay. So if there's an x in both the base and the exponent, 100% you have to use this logarithm trick. There is another way of doing it, but it's effectively the same thing, where you write x to the x as e to the x ln x, right? But those are basically the same trick. Okay. And Michael, yeah, sure, we can do that just because it's on topic. And don't worry, somebody, Camilla, I saw your questions, so they're in the list. So I know. No problem, Abdurrahman. See you later. So let's do 2 to the x. Yeah, can I scroll up? Sure. So just let's do 2 to the x real quick. Just because while we're here talking about logarithmic differentiation, this is probably a good time to do it. Okay. So Haley, you got it? You're good?
Tyler, there's a hand raised. I don't know if you saw it.
Okay, Kevin, what's up?
I still didn't get like how I got C a while ago. You said you just put it in octave. Like, can you like quickly go over that? Like, show how you plug that in octave to get -5 in 1?
Sure. Let me do the 2 to the x, then I'll do octave, and then Camilla, I'll do your questions. Okay. So let me do the 2 to the x question first, Kevin, and then I'll do the octave one. Okay. So Michael, it depends. First of all, so I assume by this you mean 2 to the x like this, right? Because exponentiation is non-associative. So we have to be really careful about putting those brackets there if we want that to be that. Okay, cool. All right. So actually, you know what? Let me call this function maybe h of x first. So what I'm going to do is I'm going to define a function f of x to be 2 to the power of x, in which case this function is f of x, right? Because it would be 2 to the f of x, which is 2 to the x. Does that make sense? So this function is the double composition of f with itself. So if I want to then differentiate this, so h prime of x is f prime f of x times f prime of x. And let's remind ourselves over here, f prime of x is ln 2 to the x, right? So if I plug that in, I'm going to get ln 2 to the f of x, which is 2 to the x, times, so that's the first bit, ln 2 to the x. Okay, and like I said, that's probably good as it is, but if you want to do a little bit more simplification, certainly you could gather the ln 2's together, right? And you get ln 2 squared. And then if you want to be really clever, you can say that this is plus x rather, right? Then if you multiply two things with the same base, you can add their exponent. So you get 2 to the 2x times 2 to the x. So that gives you 2 to the 2x plus x. You don't have to do that. You can leave them separately. But if you really want to simplify and get clever, you can add their exponents like that. Okay, does that make sense? No problem. Okay, let me very quickly do octave, and then Camilla, we're going to do your questions. I'm sorry that I keep pushing them back. We will do them very quickly here. All right, so let me jump to a new, all right. Okay, so remember we had the equations C plus D. This is going to throw an error, but I'm just going to write them in so that we have it, right? That you can't actually solve it like that, but I just want them so that they're on the screen and so we know what they look like. So what I'm going to do is I'm going to create a matrix, the augmented matrix, which describes this system like that. And then in octave, I can just say find RREF, and here are your solutions here. Here is C, and here is D.
Oh, okay.
Do you remember doing that from like the linear algebra days?
Yeah.
Yeah, so you might have to go back and do a little bit of reviewing of that. The other thing that you could do is you could say like, let's let this be the coefficient matrix. And then B is -4, -19. Oops. And so we wanted to solve ax equals b. So we do the inverse of a times b like that, and that would give us our solutions as well. All right, so all of those work in terms of using Octave to solve your systems. Like I said, you might have to go back and look at what you were doing in the linear algebra days, but it's not bad. Wait, the second one? Okay, so remember one way of writing down matrix equations was as ax equals b, right? And then in that case, that would tell you that x was equal to a inverse times b, right? That was the theory when we did linear algebra. Yeah. So what I did is inverse a times b is exactly that, right? That's a to the inverse times b, and you do that, and that gives you your solution. Yeah. Yeah, like I said, it's been a while, right? It's probably been like 4 to 5 months since we did this last. So obviously there's going to be a little bit of rust there. Solving linear systems, super important, right? And again, all of Google works by like eigenvalues, eigenvectors, linear systems, and stuff like that. There is a lot to know. Okay, so I promised Camilla.
Thank you, Prof.
Yeah, no problem. So I promised Camilla we would do week 5 pulls 7 and 11 you wanted to know, right? So 7, yes, okay. So, I gotta share this one. So this is pulls week 5 question 7. And it said to differentiate ln of x plus 1, x plus 2, x plus 2021, like that. Okay. Yeah. Oh, yeah. That's a good point. I should probably stop recording.